structure of the molecule. The molecule structure is this guy, okay? So that's an amide, okay? It's an amide. And most directly, right, it would be easy to get from acetic acid because it's a derivative, right? If you think about, did I say acetoacetic? I meant malonic. My point is from acetic acid, which has to have started at malonic ester, okay? So in this case, to get to the derivatives, yes, absolutely. If you have a derivative, it's almost going to, surefire, it's going to be this malonic. So you've got to do the malonic looking at not this side, right? This side you're going to ignore because that's what you're going to work with after. You're going to start on this side and say, I know that this and this come from malonic ester. What did I need to add as an R group? Obviously CH3 here, okay? That's what I needed to add. So the steps to synthesize this would be what you'd be asked on an exam. Show the starting material. You're going to show malonic ester, okay, as your starting material. So malonic ester is this guy here, right? So you'll put this in the box that says starting material. And then it's going to ask for your synthetic steps. I'll get you in a second. So at this point, you're going to add NaOET. You're going to add CH3Br. Okay, that adds your CH3. This guy out here. Okay? Now you got to get back to the acetic acid because now you're on to the conversion part, right? So to get back to the acetic acid, I'm just going to move up here. 3 here, you need to hydrolyze. So you do something like NaOH and H2O. You now heat it up. When you heat it up, the carboxy group leaves and you're left with acetic acid. And the last piece is to do the final conversion, right? Which is to get to something I know, something above an amide in the table, either with thionyl chloride to the acyl chloride, or Fischer esterification to get to the ester. Either is fine, okay? But I'm going to go with thionyl chloride. And finally, the conversion down to your final product, which obviously would need excess. Your question in the back.
Yeah, would both of the metals coming off that nitrogen be a part of the same circle on the HO bond?
Okay, so you see how it says 3H and 3H? They actually are distereotopic. That's a blast from the past, right? Yeah. And nitrogens can be tetrahedral, they can be chiral centers because the electron pair counts as a separate attachment. In this case, it's a prochiral center. You have an electron pair, the carbonyl, and 2 methyls that are the same. But because it's locked in one way, they're distereotopic. It's just, yeah. So they generally come off as 2 different signals. Okay? So that's where that comes from. And I would know that they're there because they're at 3, right? So they have to be off the nitrogen. So anything that's up between 2 and 3 is off a carbonyl, is off a nitrogen, or is off a benzene ring. Those are really my 3 choices. Okay? So that's how I got down to that. Okay, great. So derivatives, obviously. The other one that's easy to get to are primary alcohols. You can take a carboxylic acid and get down to a primary alcohol with lithium aluminum hydride. Okay? From acetoacetic ester. Okay, I'm not going to be exhaustive up here, but you can be exhaustive in your notes. You can get to ketals and then and acetals and all the hemis, right? So you can get to a hemiketal, a hemiacetal. Well, actually, you wouldn't even be able to get to the acetal, right? So I guess a hemiketal or a ketal. That would be using an oxygen nucleophile. You can get to an imine or an enamine. That's using a nitrogen nucleophile, either a primary nitrogen to get to an imine or a secondary nitrogen to get to an enamine.
What is it they use for
These are oxygen nucleophiles, right? Oxygen, so alcohols as nucleophiles, right? What else can you do? You can get to secondary alcohols. That would be using a reducing agent like lithium aluminum hydride or sodium boryl hydride. That gets down to secondary alcohols. And you can get down to tertiary alcohols by reacting with a Grignard. Okay, if I take a Grignard and react it at ketone, I get a tertiary alcohol. I can't directly get to a primary alcohol from acetoacetic ester. Okay? So I asked you to do this thinking because you will have one of these final products, right, that you'll need to backtrack like we did today to figure out what the a 10 to 10 to 15 point question on your exam. Are there questions about this type of question? Okay.
How'd
Yes.
you say you could get tertiary alcohols? I missed that.
Tertiary alcohols come from taking a Grignard and reacting it at the ketone, right? Okay. All right. Which of these nucleophiles will not undergo a Michael reaction? Michael reactions are ones that do conjugate addition, right? Conjugate addition. So last class we learned that there really is a pKa cutoff. We were talking about this. There's definitely a pKa cutoff. Things that do conjugate addition, which really is the Michael reaction, right? Michael reaction is reacting at this electrophile, right? That's the Michael reaction. When this carbon that I have an arrow pointed to is your electrophilic carbon, it's called conjugate addition. It is the Michael reaction. Things that do this are moderate and weak nucleophiles, okay? So if I take a scan here, I only have A and D that would classify as being Michael addition, okay? Because I scanned through. A comes from that nucleophile that's sandwiched between two carbonyl-like species. That pK is 9. It's considered moderate, right? Anything between 0 and 11 for the pKa of the conjugate acid is moderate. Anything between 0 and 11. And all those sandwiched nucleophiles are between 0 and 11. They're all 9 or 10. Some of them are even a little bit lower. The organolithium, B, its conjugate acid is just an alkane, 60, strong. Definitely not doing a Michael reaction. It's gunning right for the carbonyl center. C is sodium borohydride. Sodium borohydride, H minus, comes from H2. And H2 is the conjugate acid, pKa around 40, right? Definitely strong, gunning for the carbonyl. And the last one is our amine. Conjugate acid is the protonated version. pKa is 9, also moderate, and is going to do a Michael addition reaction. So both A and D do Michael addition, using this as my electrophilic center, getting the thermodynamic product, and B and C come and attach with the carbonyl. Okay? You are tested on your ability to understand which ones are going to do Michael and which ones are going to do direct addition. There is a section in your chart, in your webs, that actually tests this piece here. Okay, so make sure you review that. Yeah.
So when you were discussing Michael addition in the notes, that 1,2 addition isn't actually Michael?
No. So the 1,2 addition is a direct addition at the carbonyl. Michael requires this center that I pointed to right here as the electrophilic center. So this is the start. This is Michael addition is considered 1,4 addition. Okay? This language is sometimes just relegated to clickers, because really on an exam, you'd see this as a starting material, right? And then you'd see some nucleophilic choices, and you would either choose to do Michael, right, 1,4, or choose to do direct, 1,2. You wouldn't be questioned, show the Michael addition product or anything like that. Yeah? It's similarly concepted, yes. Yes, it has to do with what's the most likely site for reactivity, yes. And those really strong nucleophiles, they are gunning right for those carbonyl centers, okay? So organolithiums, Grignards, hydride reagents, those are guaranteed to go right in for those carbonyl centers, okay? Yes?
So Gilmans are among the class that are moderate to weak nucleophiles.
Gilmans, yes. Gilmans are soft nucleophiles. You couldn't do the conjugate acid argument, right? Because you can't really do that. But yes, they are diffuse in charge and hence are considered moderate. That's a great question. Gilman reagents, R2CuLi, they react in a Michael fashion. Gilman's attack right here. The R group attacks right here at this electrophilic center. Yeah?
When you talk about Michael reactions, that's only referring to conjugate addition, not direct addition?
Correct. Michael reaction is conjugate addition for sure. But again, on an exam, right, you're going to see something like this, You would see this molecule, and you would see strong nucleophile, weak nucleophile, and you'd be showing the conjugate addition product for this weak nucleophile and the direct addition product for the strong nucleophile, okay? Which is what we talked about in class, okay? So just make sure you know weaks and moderates do conjugate addition, 1-4. That is the Michael reaction. The others do the 1-2. Yeah,
Did you say for the lithium, the conjugate base was about 60?
60. Yes, an organolithium is like a Grignard,
Okay.
okay? Similar to a Grignard. Okay, great. So 3 was asking you to order the steps to get to this final product. So it was using that sandwiched nucleophile here. So to get to this nucleophile here, you can't use NaOH. If you use NaOH, it's going to do hydrolysis first, okay? Or correspondingly, while it's deprotonating, it's also going to do hydrolysis. So you have to be very careful with the types of bases that you use here in these central portions, okay? So step 1 is NaOET. It needs NaOET to get this nucleophile here, okay? This nucleophile does Michael addition. So you take this center here, and it attacks at the 4th site, moving the double bond over, okay, to get to now this here, okay? This is the product here. Direct product, right? Okay? The next step is to add NaOH. Okay? You add NaOH, and it's going to hydrolyze and actually keep on going. So watch what happens. You're going to hydrolyze first. This is the hydrolysis center, right? The nitrile belongs in the carboxylic acid family paired with the amide, and it hydrolyzes back to a carboxylic acid, where the carbon of the nitrile is the carbonyl carbon of the carboxylic acid. So, upon first use of OH minus, you get down to, there's water in here too, so we're gonna move back to this. You're gonna get to this guy here. Okay? Still base in here. You heat this up. There's a bunch of things that are going to happen. First, you're going to see decarboxylation. So you get down to this guy here. And finally, you see an intramolecular aldol. Which does our alpha beta unsaturated formation. I'm one off my carbonyl. I'm moving fast. Sorry. Trying to get through. Yeah.
Heat is what's favoring decarboxylation. We added the down step, and then it does the cyclization on its own.
Yep. Yep.
Where did that negative charge come from?
This one here.
Yeah. No, the one below.
Before the
Oh, okay. I'm like, I don't see another negative charge.
Yeah.
See, I am going crazy. You could really be like, do you see that? Okay. This came from NaOH. Okay. So really, what you have is a bunch of stuff in the flask, right? You add NaOET. Doesn't matter if the NaOET is there after the first step. You dump in now stuff to ensure the hydrolysis, decarboxylation, and then an intramolecular. It's very, very confusing. So all you're doing is adding base. And when you add base, tons of things can happen, right? Tons of things can happen. Yep. Yeah, yes. Okay, yeah. I cleared that when we added the NaOH, right? There's water in the flask now, so I cleared it. Yeah. Okay. All right. So this is about intramolecular reactions. It's about reminding you of this very special nucleophile for Michael additions. Okay? This is a special nucleophile, not one I put out on the board the last class, and I want to make sure that I'm doing everything that I'm supposed to up here. And this is a very special nucleophile and often used in Michael reactions. So, somewhere here on the board, oh, here it is. So, in terms of the product that you get in the end of a Michael addition, this actually is a 1,5-oxo product. A 1,5-oxo product, okay? If you look here, and I count out starting at 1 carbonyl, 1, 2, 3, 4, 5. A 1,5-oxo product always results from a Michael addition, okay? So you know on your homework you had those 2 molecules that said, show what you used to make this aldol product, show what you used to make this Claisen product. This is another added fold. Show what was needed to make this Michael product. There are questions to try on the weekly quiz. I definitely suggest trying them, okay? Michael additions, you can tell it was Michael because you get a 1,5-oxo product. Claisen again was your 1,3-oxo for your standalone ketones, and the aldol was the alpha-beta unsaturated or the beta-hydroxy ketones or aldehydes, okay? So, you need to be able to look at your product, discern it into one of these categories, and then backtrack to figure out what was needed in a Michael or a Claisen or an aldol. I remind you with the Michael additions, you must be using these sandwich nucleophiles. Michael addition doesn't work that well to use, say, a nucleophile like this. This nucleophile, which you can use in aldol, you can't use in Michael because its pKa of the conjugate acid is 16. It isn't going to do only Michael, okay? So when you backtrack, you have to create these sandwich nucleophiles that have carbonyls on both sides, a carbonyl and a nitrile, an ester and an ester, whatever it is, it has to be sandwiched between 2 carbonyl-like carbons, okay? There's tons of practice, not on the most recent weekly quiz, but the one just prior, okay, about getting to these Michael products. Are there questions about this? Okay, moving on. It said, which one of these is going to hydrolyze more quickly? Okay, the bottom line is this. When you do the hydrolysis of an ester and an amide, so methyl acetate gives me acetic acid and methoxide at the end, which does an acid-base chemistry step, right? That's what makes it irreversible. You know that base hydrolysis is irreversible for both amides and esters, and acid hydrolysis is only reversible for the esters. This last step is what makes it irreversible. You get out, at the end of the reaction, a carboxylate and a neutral alcohol. pKa of that alcohol is 16. What you had coming in was 5. Okay? If you look at the amide, the end of the amide hydrolysis, right, directly from tetrahedral collapse, I get this guy, okay, and acetic acid, and acetic acid. And this also does acid-base chemistry very quickly. The pKa here is 36. The pKa here is 5. Which one of these do you think is more complete? Using what you see on the board, which one sits more to the right, is thermodynamically driven? Which one?
Right.
The one on the right. That's exactly right. Okay? This is how you tackle a question like this. Wink, wink, nudge, nudge. This is what you do. So you're asked about hydrolysis, right? Say I'm asked about hydrolysis on the test. The first thing I'm going to know is the mechanism for hydrolysis, because I'm not going to come to that test without knowing the mechanism for hydrolysis. The second thing I'm going to do is if I'm asked about complete hydrolysis, I'm going to look at the acid-base chemistry at the end. And I'm going to be able to write out these reactions with pKa's to make a statement. I can't nudge, nudge, wink, wink, enough. Okay, so next question was using H2S. It was asking you to make a thiol, right, as opposed to a thioester, I guess, instead of an ester. This is also acid-base chemistry, right? Lots of acid-base chemistry. So this is asking you to go from some anhydride, because I asked you to switch it, with H2S to get down to something like this. Okay? Now, we talked about these problems, and these hydrolysis, or these interconversions problems, we've talked about a lot. Okay, so you should be able to analyze this type of thing. When you do this here, you want to always check to know how much nucleophile to add. You're always going to check your protonated nucleophile, right? So your protonated nucleophile is something like this, right? And I can see there might be an error in my, okay, and your leaving group. What's my leaving group here is acid base. Okay? And my leaving group. Okay, this is my acid-base step. Always be able to do the hydrolysis reaction by taking the nucleophile, attacking it at the carbonyl center, collapsing for the better leaving group to leave, and then taking your protonated nucleophile and your leaving group and running the acid-base reaction. So in this case, you get to this and acetic acid. Acetic acid is definitely 5. We are going to need to take a guess on this guy. What do we want to guess? Something less than negative 1.7. So we'll go less than that. So I don't know, negative 4. I'm going low, right? So which way does this go? To the right. So what is the correct answer? Do I need excess nucleophile? No, I do not.
You said yes.
You said yes.
I know I said yes. Aren't you listening to my, I have it on recording here. I did say there likely was a mistake in the circling on the way over. I did say that out loud. This is the acid-base step, right? Yes.
You compared the thionyl, whatever it's
There's
called.
a question here. Yeah.
You compared that to an ester. Why wouldn't you compare that to a carboxylic acid?
Oh, you can compare it to a carboxylic acid as well. Yeah, I mean, it doesn't matter in this case, yeah.
Yeah.
Uh-huh.
You also said that just to go down one step, you don't need excess as well.
Okay, be careful about that go down one step, because the examples on the test, right, are going to generally be a trickier one.
Of
So
course.
you got to be ready for it,
Of course.
right? I'm being honest, right? Here I am being honest. My honesty falls at this. Don't get thrown by whatever crazy nucleophile is there, right? Take the nucleophile, the nucleophilic atom, the one that's got an electron pair. Attack the carbonyl center, right? Push up the electrons. Deprotonate it with the same nucleophile, collapse the intermediate, and check the acid-base chemistry between the protonated nucleophile and the leaving group. And if it sits to the right, the answer is no, I only need 1 mole. And if it sits to the left, the answer is yes, I need more than 1 mole. This is something we did again and again and again, and there's about 10 examples, right, from the workshop. The answers are already online, okay? So this is your choice. You learn this or you shoot yourself in the foot. That's I don't know which option
I thought you
you'll
were going to
choose,
say shoot
but-
yourself in the face.
And I'm not suggesting to go do that. Just to be a public service announcement here. Okay. The next question was a trick question. Question 6 says, which conversions can use a charged nucleophile? You can use a charged nucleophile to get back to a carboxylic acid, right? You probably all answered, though, correctly D, right? D. That's great. Good to know. Someone tell me why you can use a charged nucleophile to go from an acyl chloride to an anhydride.
Because it's a good leaving group.
Because it will not deprotonate the alpha site. That's absolutely right. Because it will not deprotonate the alpha site. Okay? And question 7, the answer was A. See if you can work through those. The answer was A. All right. There's a few more things I want to say, okay, before we move on. Number 1. This is my derivatives chart here on the left. Very quickly, going down, does the electrophilicity of the carbonyl carbon, does it increase or decrease? Decreases. Good. Does the ability for that R group, right, the Cl versus the acetate versus the OR, does the leaving group propensity, the ability to leave, increase or decrease?
Decrease.
Very good. The alpha hydrogen, does the pKa of that guy increase, meaning go toward 100, or decrease, go toward 0?
Decrease.
It increases, right? It goes toward 100. We start out at something like, we don't know exactly, but somewhere around probably 12, 10, 12, right? We come down to probably something like 14. We're down here to 25. We're up here at 30. Which proton's more acidic in the amide? The one on the nitrogen, right? Because it's off an electronegative atom. Good. Okay, you're going to get those questions right. Okay, we did this. Alkylation. You all know about using thermodynamic and kinetic enolates, right? To alkylate. Using temperature to choose the side that you alkylate. That's question 2.